Hi students, in this video we're going to go over section 1.7, variations of the conditional. So we've already gone over the conditional statement in the previous section. So in this section we're going to discuss variations for the conditional statement, which are going to be your contrapositive, converse, and inverse. And we're also going to look at sufficient and necessary conditions, which are related. So this table here summarizes all the variations for the conditional statement. We have the formal name, the symbolic form, and then how you would read it. So the first one listed here is just the conditional statement that we've seen before. So this was the symbolic form we had, and we would read it as if P, then Q. That's the original conditional statement. The second one we have here is what we call the converse of the conditional statement. This is where your P and your Q are swapped. So we would read this as if Q, then P. So we're switching our hypothesis and conclusion. Then you have the inverse of the conditional statement. And this is where the P and the Q here from the original are negated. So it's read as if not P, then not Q. And then the last one is your contrapositive of the conditional. And this is where the P and the Q from the original are swapped and negated. So it's read if not Q, then not P. So those are the variations for your conditional statement. Example 1. Write in words the converse, the inverse, and the contrapositive for the following conditional statements. So for part A, we have, if Joey can run a mile, then Joey can run to Mikey's house. All right, so I'm going to copy that over so I have a little bit more room here. If Joey can run a mile, then Joey can run to Mikey's house. Okay, so this part here, Joey can run a mile, that's going to be the P. And then this part here, Joey can run to Mikey's house, that's the Q. Okay, so that's our current conditional statement. So we're going to write the converse first. And with the converse, you're just swapping the P and Q. So this is going to be if Joey can run to Mikey's house, then Joey can run a mile. Then the next one is going to be the inverse. And this is where you just negate the P and the Q from the original conditional statement. So this is going to be if Joey cannot run a mile, then Joey cannot run to Mikey's house. And then the last one is going to be your contrapositive. And this is where the Q and the P are switched and also negated. So this is going to look like if Joey cannot run to Mikey's house, then Joey cannot run a mile. And when you're doing these, make sure you do title, label each of these statements, each of these conditionals. So make sure you clearly put down which one's the converse, the inverse, and the contrapositive. All right, now we're going to try part B. If it is windy, then Kelly does not go sailing. If it is windy, then Kelly does not go sailing. Okay, so this part here is windy, that's our P. And then remember, we don't include negations in our simple statements. So Kelly goes sailing is the Q. So if you have Kelly does not go sailing, that would be the negation of Q. So that's the current form for the conditional statement we have. So when we do our converse, we'll do the converse first. This is where you just swap the hypothesis and the conclusions. So this is going to be if not Q, then P. But I want to write that out in words. So this is going to look like if Callie does not go sailing, then it is windy. And then the inverse is where you negate, you take the original conditional and you negate both the hypothesis and the conclusion. But here, because we're going to have a double negation, we're just going to write that as a Q. Instead of a double negation on Q, we're just going to write Q. So as we put this in a sentence, it's going to look like if it is not windy, then Callie goes sailing. Remember, the Q is Callie goes sailing. And I just realized that I spelled then wrong because I missed the N up here. We'll just fix that. And then the last one is your contrapositive. So this is where we're going to both switch the hypothesis and conclusion and negate them. So it's going to be not Q, right? If not Q, then not P. But that seems a little silly, so we're going to write this in equivalent form using our double negation law to write if Q, then not P. And then in sentence form, this is going to be if Callie goes sailing, then it is not windy. Example 2, write the converse, inverse, and contrapositive for the following conditional statement, and also determine whether the conditional, converse, inverse, and contrapositive are true or false. So our original statement here is if a natural number is divisible by 5, then the natural number is divisible by 10. So P here is a natural number is divisible by 5. And then Q is the natural number is divisible by 10. That's the current conditional statement we have. All right, so we're going to go ahead and we're going to do the converse first. So that's just where we swap the P and Q. So this is going to be if a natural number is divisible by 10, then the natural number is divisible by 5. Then we're going to do the inverse. I'm leaving some space because we're going to go and write out if these are true or false after this part. The inverse is just negating the P and the Q from the original conditional statement. So it's going to be read if a natural number is not divisible by 5, then the natural number is not divisible by 10. And then the last one is the contrapositive. So maybe you want to pause the video for a second and see if you can write out what the contrapositive would look like. And then once you've done that, let's check it. The contrapositive is where you switch the P and the Q and you also negate them. So as a sentence, it's going to be read as if the natural number is not divisible by 10, then the natural number is not divisible by 5. This is the most writing you'll ever do in any math class, by the way. And we're just getting started. All right, so now we're going to go through each of these 4 statements and figure out if they're true or false. So we're not doing formal proofs yet. We'll talk about proofs. We'll get into proofs in later chapters. So right now, we're just going to kind of talk these out and use our knowledge, what we already know about divisibility, to figure out if these statements are true or false. So this first one, if a natural statement is divisible by 5, then that natural number is divisible by 10. So is it true if you have a number and if you can take that number and divide by 5, are you basically guaranteed to be able to divide it by 10 also? And if not, we'll come up with what's called a counterexample to disprove it. And we'll go over counterexamples in more detail in a later chapter. But for now, we're just going to write false. This is not true. And this is because the number 15, for example, is divisible by 15. Is divisible by 5, right? We know we can divide 15 by 5. But 15 is not divisible by 10. You can't divide 15 evenly by 10. So the overall conditional statement, that conditional statement is false because what we're showing here in this counter example is technically what we're doing. We're showing that the hypothesis is true. 15 is divisible by 5, but the conclusion is false. 15 is not divisible by 10. And we know from our truth tables of the conditional statements before, when we went over it, if you have a true hypothesis and a false conclusion, then the overall conditional statement is false. So later on, when we get into it, this is what we'll refer to this as a counterexample. We're disproving something. Okay, let's look at the converse. If a natural number is divisible by 10, then the natural number is divisible by 5. So if we have a number and we can divide that number by 10, are we guaranteed to also be able to divide that number by 5? Think about it for a second. And this would be true. And this is because any number that is divisible by 10 must also be divisible by 5, since 5 is a factor of 10. So that one's true, right? If you have the number 20, you can divide that by 10. You can also divide by 5, right? Because 10 is 2 times 5. All right, then we have our inverse. If a natural number is not divisible by 5, then the natural number is not divisible by 10. Is this one true, or is it false? If it's false, we have to be able to come up with an example to disprove it, a counterexample. Well, let's think about it. If it's not divisible by 5, then the number is not divisible by 10. Can we come up with a counterexample? This one's true. And this is because any number that is not divisible by 5 cannot be divisible by 10, since 5 is a factor of 10. Notice the similarity between the converse and the inverse when you're writing out explaining how it's true. So for example, if I've got the number, let's do like 32, I can't divide that by 5. So there's no way I can divide it by 10, because 10 is 5 times 2. And then the last one, think this one through too before I write something down. So if the natural number is not divisible by 10, then the natural number is not divisible by 5. Is that true or false? Does it make sense? Or do we think that that's false, and can we come up with an example to show that it's false? So this one's false, and this is because, we'll give an example. I'm going to use 15 again, like I used in the very first conditional statement. This is false because 15 is not divisible by 10, but 15 is divisible by 5, right? So here we have basically we're showing that the hypothesis is true, 15 is not divisible by 10, and then we're showing that the conclusion is false, 15 is divisible by 5. So our conditional statement, even if it's a contrapositive but still conditional, would be false because you have a true hypothesis and a false conclusion. And then let's go back to the first one. So you see how the truth value for the conditional statement and the contrapositive are the same. Both of those were false. And notice how the converse and the inverse, the truth values for those statements, had the same truth value. Both were true. So this table here provides the truth table. This is like a large combined truth table, but it shows the truth tables, the truth values for the conditional, the converse, the inverse, and the contrapositive. So if you look at the conditional and the contrapositive, those are logically equivalent. They have the exact same truth values down their main columns. So we can say if P then Q is logically equivalent to if not Q, then not P. They're logically equivalent. And then look at the truth values for the converse and the inverse. They are the same. So those two statements are logically equivalent. So if not Q, or I should say if Q, then P is logically equivalent to if not P, then not Q. So our truth values for the previous example should make sense now that we're looking at this. Okay, the last thing we're going to do in this section is go over definitions for sufficient and necessary conditions. So if R and S here are statements, this first bullet here says that R is a sufficient condition for S, means that if R, then S. So if we have this conditional statement, if R, then S, R is a sufficient condition for S. This means that the occurrence of R is sufficient enough to guarantee the occurrence of S. So let's do like a mini example. Let's say R here in this case is Bongo is a dog, and S will be Bongo is an animal. So this conditional statement would be if Bongo is a dog, then Bongo is an animal. So being a dog is a sufficient condition for Bongo to be an animal. And now let's look at the other one. So R is a necessary condition for S, means that if not R, then not S. So symbolically, that would look like this here. If not R, then not S. Or, because we've already seen that the contrapositive and the conditional are equivalent, you could also write it this way. If S, then R. And so for R being a necessary condition, that means that if R does not occur, then S cannot occur either. So you basically can't have S without R. And then let's do another mini example. So let's say arg is Ted is at least 35 years old. And then S can be Ted is president. So if I'm reading this statement here like this, it would be if Ted is not at least 35 years old, then Ted is not president. Or equivalently, I could say if Ted is president, then he is at least 35 years old. So to be president of the United States of America, you have to be at least 35 years old. That is a necessary condition, a condition that has to be met in order for you to be president. All right, let's do one more like mini example before I go to the example on the slides. So let's say if it is raining, then the ground is wet. So I'm going to have P be it is raining, and Q is going to be the ground is wet. So in this case, raining is a sufficient condition for the ground being wet because rain causes the ground to get wet, right? So let's put down that P is sufficient condition for Q in this mini example. And then the ground being wet, Q, is a necessary condition for it having rain. So Q is a necessary condition for P. So if it rained, then the ground must be wet, assuming no other context in this example. And maybe if you think about it in its contrapositive form, it'll make more sense, right? If the ground is not wet, then it did not rain. And you can take this a little bit further too. You can say it is raining, the raining part, that we know it's a sufficient condition. It's not a necessary condition because it's not the only way that the ground can get wet. And you can also look at Q We know it's a necessary condition for P, right? The ground being wet is a necessary condition for it to have rained, but it's not a sufficient condition. The ground being wet is not sufficient enough to say that it rained. So our last example, write in words the following statements as conditionals. So for part A, I'll squeeze it in up here. Kelly's birth on U.S. soil is sufficient condition for her to be a U.S. citizen, right? It's a sufficient condition. It's not the only way that she could be a U.S. citizen, but if she is, then she is guaranteed, if she is born on U.S. soil, then she is guaranteed to be a citizen. So we will write this as if Kelly is born on U.S. soil, then Kelly is a U.S. citizen. And then for part B, having gasoline in the car is a necessary condition for the car to start. I'm going to do this a couple ways. So for part B, one way to write this is if the car starts, then there is gasoline in the car. Or you can write it as the contrapositive with the negations. So it could be if there is no gasoline in the car does not start. So either of those is acceptable. All right, we're done with this section on the variations of the conditional statement. Try out the homework and I'll see you in the next video.